Welcome back. In this section, we'll be talking about symmetry of graphs. So if we're thinking about any equation that we might be graphing, it's possible that there might be one or more kinds of symmetry that the graph might show. And so what we're going to talk about here is how we can detect that using algebra. How can we tell that an equation, when I graph it, would show symmetry in the x-axis, or symmetry in the y-axis, or symmetry about the origin? To start with, if we're thinking about being symmetric around the y-axis, so around the x-axis rather, so maybe something like this shape, that might be something that's symmetric around the x-axis. If you're symmetric around the x-axis, then any point that you might have on the graph, you're going to have its mirror image reflected across the x-axis. So if you have an xy point, you'll also have a point with the same x-coordinate, but with the opposite sign for the y-coordinate. So for example, if you knew the point 4, 1 was on the graph, you'd have to have also the point 4, negative 1 for this to be symmetric across the x-axis. And that actually is both a description of what symmetry across the x-axis means and also a way to test for it. What we would have to do is ask ourselves, if we replaced every y with a negative y, do we get the same equation back? If we modified our equation by replacing all the y's with negative y's, is it the same equation? If that's true, then that's telling you that any xy point on the graph, there would have to be also one with a equivalent negative y, but with the same x. And so that's what we'd have to test. So something like this graph of x equals y squared, you can see that it's symmetric around the x-axis, but I want to show this using algebra. And so what we need to do would be, for that equation, we're going to replace the y with negative y, and we ask ourselves, do we get the same equation? So if I take that equation and replace y with negative y, so I would have x equals to negative y all squared. And if I were to look at that negative y and square it, that would just be the same thing as y squared, because of course negative y times negative y would be positive y squared. This is exactly the same thing as the original equation that we started with, which means that if we have an xy point, we would also have an x negative y point. In other words, this is something that is symmetric across the x-axis. And we can say the same sort of thing about symmetry across the y-axis. So if we're symmetric across the y-axis, so imagine something looking like this, then for any xy point that you might happen to have on the graph, you would have one with the same y value, but with the opposite sign for the x value. In other words, if you have an xy point on the graph, you should have a negative xy point on the graph as well, which means that if your graph is symmetric across the y-axis, then if you replace every x in the equation with a negative x, you should have something equivalent to that original equation. So let's take a look at this example. Here is a graph of a nice little polynomial function, y equals x to the 4 minus 6x squared plus 4. And visually it looks symmetric across the y-axis, but now we're going to confirm with algebra that it is. And so what we'll do is we're going to take that equation and we're going to replace each x with negative x. And so what do we get? Well, we'll get y on the left side. We'll have negative x to the power of 4 we'll have minus 6 times negative x to the power of 2, and we'll have plus 4. And if we simplify this, negative x to the power of 4 is just x to the power of 4, and negative x to the power of 2 is just x to the power of 2. So this actually simplifies to give me y equals x to the 4 minus 6x squared plus 4, which, as we notice, that's exactly the same thing as our original equation, which means that we have something that's symmetric across the y-axis. So we've got two kinds of symmetry that we've seen so far. So symmetric across the x-axis, we have symmetric across the y-axis, and there's a third kind of symmetry, which we call being symmetric about the origin, and that one's maybe not as easy to express in words, but it's kind of easier to show with a drawing. When we say that something is symmetric about the origin, what we're really saying is that it looks like it's been reflected twice. So if I have a shape like this, and I reflect it once in the x-axis, it would be there. But then if I take this and now reflect it in the x-axis, it would be down here. So something like this kind of a shape, you could imagine this as being symmetric around the origin, that if you took this chunk and flipped it in the y-axis and then flipped it in the x-axis, you would have this equivalent chunk down below. That's what we mean when we say that something is symmetric about the origin. And so what that really means for us as far as algebraically, if you have a point that's on your graph, because it's really flipped twice, reflected in the y-axis and also in the x-axis, then you'd have to have a point with the opposite sign for the x and also the opposite sign for the y, because flipped in the y-axis and also reflected in the x-axis. In other words, you would have to have a point negative x and negative y also on the graph. So that means that if we want to test for being symmetric about the origin, we'd have to check what happens when we replace every x with a negative x and also every y with a negative y. Do we get our same equation back? If so, good for us, it's symmetric about the origin, and if not, then it's not symmetric about the origin. So something like this, we have y equals x cubed over 9, and we want to show that it's symmetric about the origin using algebra. Visually, we can see it's symmetric around the origin. If we took this little piece here and reflected it in the y-axis, then reflected that in the x-axis, we would have that other part of our graph. So it does look like this is symmetric about the origin, but let's now show this. So here we're going to replace y with negative y, and we're going to replace x with negative x. And the question is, do we get something equivalent to our original equation? So for the original equation, I'm going to replace the y with negative y and the x with negative x, and that would give me a negative y on the left side, and on the right side, negative x cubed over 9. Now, negative x, when you cube it, that's negative x times negative x times negative x. That would be negative x cubed. And if I were to take this equation now and multiply left side and right side by negative 1, you would have y on the left side, and you would have x cubed over 9 on the right side. And you could see that what we have is the same as the original equation. So when we replace the x with negative x, when we replace the y with negative y, we got our original equation back. So we can say, yes, this is symmetric about the origin. So notice here that for all three types of symmetry, we're basically doing a little substitution to check that If it's symmetric across the x-axis, that means replacing y with negative y leaves us with the same equation. For symmetry across the y-axis, replacing x with negative x, does that leave us with the same equation? And then finally, symmetry across the origin or about the origin, if we replace the x and the y with a negative x and negative y, do we get the same thing back? So now the kind of obvious thing here is that although these three graphs that we looked at, they were all nice and symmetric, not everything is symmetric. So for example, even something very simple like a nice little straight line like this is clearly not symmetric across the x-axis, that what's down below is not just the mirror image of what's above. It's also not symmetric across the y-axis. What's on the left side and what's on the right side are not mirror images of each other. And also it's not symmetric about the origin because, again, if you imagine taking part of this graph and flipping it in the y-axis, then flipping it in the x-axis, we don't have the same thing showing up down there. So no, it doesn't appear for that straight line that it's symmetric across the origin or the x-axis or the y-axis. And in fact, most equations that we'll see don't have any symmetry. They're not symmetric in any way. So what we want to do here is show that this equation that I don't have a graph for, y equals x squared minus 2x plus 1, showing that it's not got any of the three types of symmetry. So first off, let's try substituting the y with negative y. Remember that that would be how we would test for, is something symmetric across the x-axis? And if we did that, we would see that we do not get our original equation back. We get negative y equals x squared minus 2x plus 1. And no matter what you do with that, if you multiplied everybody by negative 1, it's even more obvious that this is not the same thing as your original equation. These are not the same signs that everybody had originally. So this is something where we can say that this is not symmetric across the x-axis. And we could do the same thing for checking about symmetry around the y-axis. If we substitute x with negative x, then we would have y equals negative x squared minus 2 times negative x plus 1, which if we simplify that, we can see that it's not the same thing as the original equation. It's close to it. The original was y equals x squared minus 2x plus 1. And when we substitute x with negative x, we get y equals x squared plus 2x plus 1. So not the same thing as the original equation, which means it's not symmetric about the, or across the y-axis. And then finally, we wanted to check for symmetry about the origin. So that means we're going to substitute the x with negative x, and we're going to substitute y with negative y. So we would have negative y equals negative x squared minus 2 times negative x plus 1. And if I simplify that, I have negative y equals x squared plus 2x plus 1, which you can see that this is not the same thing as the original equation, and there's nothing that I could really do to turn this into the original equation. Even if I multiplied everybody by negative 1 to make this a positive y, then the right side would not be the same thing as the original equation. So since substituting x with a negative x and a y with a negative y did not give me the original equation back, then this is not symmetric about the origin. So that means that if we're graphing this and it suddenly looks like it's symmetric about the x-axis or y-axis or origin, then we should be concerned and have a second look at our graph. This whole business of looking for symmetry is just one of the things that we'll be doing when we're thinking about graphing things and trying to use algebra to guide our graphing. Rather than just picking a bunch of points and connecting the dots, we want to use what we know about algebra to be able to tell what should be some of the properties that our graph would have. And one of the properties that a graph might have includes symmetries.